In this video, we are going to derive the rotational inertia, once again, moment of inertia, of a couple of geometries, and by a couple I mean one. So we're going to find the moment of inertia of a thin stick, and what I mean by a thin stick is that it is a meter stick is a good model of this, and that is its mass is distributed basically along its length. Let me tell you about this stick. It has mass m and length L. So from here to here is L. And what I'm saying then is that its other linear dimensions, its height and so on, and thickness are much, much smaller than L. And so I basically ignore them and treat this as having mass distributed only along its length. Okay, obviously I can't answer this question, what's the moment of inertia of a thin stick, because I haven't specified an axis of rotation. Moment of inertia only has meaning once you've specified an axis of rotation. So the first one of these I do, I guess I'm putting the stick here, there's length L. The first one of these I'm going to do is going to be with the axis through the center of mass, which is the center of this stick. So here's my axis. I guess I've drawn this with a vertical axis, so the stick would be rotating kind of into and out of the plane of the board. If it were to rotate, I'm not going to actually have it rotate. I'm just going to have it sitting on the board, so it doesn't really matter. The axis is in the center of the stick. Okay, how are we going to do this? Well, what we have so far to find moment of inertia is, the only formula we have is for a point mass, and that is mr squared. Remind ourselves that's for a point mass, where all the mass is not distributed at all, has no length of significance. And we can't use this for a stick yet, he says. Let's just remind ourselves what these values stand for in this equation, though. M, of course, stands for the mass of the point mass, and R, remember, stands for how far it is from the axis of rotation to that point mass. We have to keep that in mind. Now, we actually have also learned that if you have 2 point masses, the total rotational inertia is found by adding up all those mr squared products. So this would be like mi ri squared, and you would sum over I. You would add up all the mr squared products for every value of I. The one we did in class, there were 2 different point masses. And so I went from 1 to 2, and we added up 2 mr squared terms. Well, that gives us a hint of how we're going to deal with this stick, because in fact, even though the stick is not a point mass, it can be turned into a nearly infinite number of point masses by feeding it through the calculus Cuisinart. And that's exactly what we are going to do. So let's actually start by defining a coordinate system, so I can define how I have cut this up in the calculus Cuisinart. I'm now drawing a coordinate system with an x-axis. I don't need any other axes because all the mass is along one dimension, just the x-axis. But I am going to specify where the origin of this is, and I'm putting the origin on the axis of rotation. That's kind of critical. So now I can say that I'm going to feed this through the calculus Cuisinart and make cuts perpendicular to the x-axis, and so I'm going to get a bunch of little tiny pieces of stick. This, of course, is looking an awful lot like what we did when we were finding center of mass of extended masses. This is a lot of what we're going to be doing is in common. In fact, it's essentially identical. The difference is that the actual equation we're going to be plugging these values into is a bit different. Okay, so I have cut this up into a bazillion little dm pieces, and I want to adapt the equation I have down here for rotational inertia of a finite number of point masses. I want to adapt that so I have an equation for a nearly infinite number of point masses. So my new equation for an extended mass, I'm going to follow the lead, is the sum of, but we're going to be adding up a nearly infinite number of products, of mr squared products. So I use the integral sign to add them all up. Okay, how am I going to write mr squared? Well, remember what these letters stand for. M, again, stands for the mass of each piece, the mass of each object. Well, these objects all have mass dm. They're infinitely small amounts of mass. So my m turns into dm. And The R value, again, stands for distance of that piece from the axis. Well, very conveniently, the distance of each of these little dm pieces, how far are they from the axis? Well, they're also that distance from the origin of my x-axis. So this first piece here, how far is that from the axis of rotation? Well, it's just this far, and that is its value on the x-axis. It's the x position on the x-axis. So basically, r becomes x. The distance of each piece from the origin is x, because that's where I put the origin of my coordinate system. So r squared becomes x squared. Doesn't have to be green, but it is. So that is our equation then for well, okay, let me back up. The more general term for the center, I'm sorry, the more general term for the moment of inertia of an extended mass you'll see in the textbook is integral of r squared dm. In this case, though, all the distances are measured along the x-axis because I have a one-dimensional distribution of mass. So my r has turned into x because I have the x-axis to label how far away things are. All right, so for this particular problem, the equation is I equals integral of x squared dm. Okay, not a big deal, but there you have it. Okay, so now I have to actually do this integral. And you remember, I hope, or if you don't, I'll remind you, that, because this is very similar to what we did with center mass integration problems a few weeks ago. We look at this and we say, I can't integrate this yet because I need to take this dm. X is a variable, all right, the variable, because each little piece of mass dm is a different distance from the origin of the coordinate system. And so I need to get dm expressed in terms of constants. X, the only variable will be x, and dx. Okay, I will do that for this problem exactly as I did with center mass problems a while ago. I find it convenient to describe the mass distribution of the stick using the variable lambda, the linear mass density, mass over length. It is assumed, I believe, and they never said this thin stick is of uniform linear mass density. It's a uniform stick. And so that means that the mass of one of these little tiny pieces, dm, is equal to the linear mass density times the length of that little piece. Remember, the length of the piece is the distance from the left edge to the right edge, which I've exaggerated here. That's not x. That's what we're talking about here. The length of the piece is dx, the thickness. So the mass of each piece is lambda times dx. There, good. So I have dm expressed now in terms of constants, lambda, x. I don't even use x to express it. I just have dm equals lambda dx. Let me just rewrite it down here. dm is lambda dx, so it's expressed in terms of constants, and dx. So now I can sub in for dm, integral x squared, and I will sub in lambda dx. And now before I do the integral, I have to recognize this is a definite integral. It's only meaningful to integrate this, to add up these values where the mass actually exists on the x-axis. So my limits of integration are the boundaries of where this mass is, of this stick. And those boundaries are the left-hand edge of the stick and the right-hand edge of the stick. Well, where are they? Remember, the stick is centered on the x-axis, so half of it is to the left of the origin, meaning the left-hand edge of the stick is located at negative L over 2. That's its address on the x-axis. And the other half is to the right of the origin, so the right-hand edge is at the value x equals positive L over 2. X equals negative L over 2 on the left. Okay, those are my limits of integration. I'm integrating from, give myself a little more room here, negative L over 2 to L over 2. Okay, now I believe I can actually do the integral and get an answer. Lambda is a constant, that gets pulled out. Integral of x squared dx, not sure this is a necessary step, but I'm doing it, L over 2 to L over 2. Okay, that's equal to lambda times. Integral of x squared is x cubed over 3. And I'll be integrating from negative L over 2 to L over 2. So now I can plug in. I equals lambda times, let's see, x cubed, I'm going to plug in L over 2. So I'm going to have L over 2 cubed divided by 2 minus negative L over 2 cubed divided by 2, close bracket, equals, I'm going to take the lambda out and put in mass over length, because I know I'm going to have to do that at some point. And let's see, I got to be careful. L over 2 cubed is L cubed over 8. And that's all divided by 2, minus negative L over 2 cubed is negative L cubed over 8, all divided by 2. So let's see, this is L cubed over I will actually now go back and fix the mistake I made. This is x cubed over 3, so these are actually over 3 over 3. Thank you very much. Over 3. Some of you have been grimacing watching me write those 2's. Yeah, okay. So this is equal to m over L. And I now have, okay, L cubed over 8 over 3 is L cubed over 24. Minus a minus is plus. L cubed over 8 over 3 is L cubed over 24. And that gives me L cubed over 12 when I add those up. M over L times, you can see where this is going, I think. L cubed over 12. Just misspelled 12. It's getting late. I'm getting tired. I want to go home. 12. And that gives me, cancel, cancel, it becomes squared. 1/12 ml squared. That makes me happy because that's what I said it was in the earlier video. We just proved it. Okay. I am going to leave it as an exercise for you to find the moment of inertia of a stick where the axis is at one end. Now you did this experiment earlier, so the axis is here. Actually, you know what would be easier would be to put the axis, oops, okay, here's the stick. It doesn't really matter. I'm going to put the axis on the left-hand edge, axis, because if you make your conventional coordinates, basically what you're going to do here is the same derivation we just did, except you're going to put the origin where the axis is here. I've said too much, and it's just going to basically change the limits. And what I'd like you to do is show yourself that when you change the location of the stick and put the axis on one edge, instead of getting 1/12 ml squared, you get 1/3 ml squared, and that will be consistent with the experiment that you did earlier. Okay. Now, there are, just in closing, there are a bunch of other shapes that we can find the moment of inertia of. There are, for instance, a disk, okay, like a huge pulley or something like that with the axis in the center that can rotate. And if it's just a big uniform disk that you put string over and have it rotate. So that's a derivation that we probably will do. I'm not going to do it now. But I am going to ask you to look at section 9-3, and there's a chart in there that actually shows you about a dozen different geometries: disk, spheres, hollow spheres like a basketball, solid spheres like a bowling ball, and some different axes of rotation. And there are some equations that we will get used to using. You'll never have to memorize them. That are derivations much like the ones we just did for a stick. For instance, a solid sphere rotated on axis through its center, such as the Earth spinning on its axis, has a rotational inertia of I equals 2/5 mr squared. And there are a number of different equations like that for different shapes, depending on their shape and depending where the axis is. So if you can just kind of take a look-see at that part of section 9-3, you'll get a sense of some of the equations we'll be using tomorrow. We're going to be calculating some moments of inertia and then moving on and doing some stuff with them. And that is about all I have to say for now, and thank you and good night.